Hello students, hello teachers, how are you? Today we are going to see second part of my presentation. Last time we were discussing about the first part of my presentation. The last presentation had uncertainty in measurement, accuracy and precision, significant figures and how to determine significant figures, the discovery of subatomic particles and the nucleus. Today we are going to see the second part of my presentation. The second part of my presentation has the following lessons. Lesson 1, balancing redox reactions using oxidation number method, limiting and excess reactants, suspensions, the difference between suspensions, solutions, and colloids. The fourth lesson, the solution process, how solution forms. Lesson 5 has factors affecting solubility. Let us see this lesson one by one. The first lesson, balancing chemical equations. Balancing using redox reactions, that's oxidation number change. Using oxidation number change, we will see how to balance chemical equations. Let me ask you a question. Try to answer the following questions. What is redox reaction? What is oxidation and reduction? What are oxidation numbers? And so on. As you know, redox reactions are reactions that involves oxidation and reduction reaction simultaneously. Oxidation is a process in which electrons are lost, and reduction is a process in which electrons are gained. The process of gaining electrons is reduction. The process of losing electrons are oxidation in chemical reaction. What is the oxidation number? Oxidation numbers are the number of electrons that are lost or gained during the chemical reaction by atoms. Redox reaction is one in which electrons are transferred from one atom to another. As I have tried to explain, oxidation is the loss of one or more electrons by an atom. Reduction is the gain of one or more electrons by an atom. This oxidation number is the number of electrons that are gained or lost when an atom combined with other atom, as well as in chemical reaction. The number of atoms of each type in chemical reaction. In chemical reactions, the number of atoms on both sides of the equation must be balanced. The number of atoms on the reactant side, the number of atoms on the product sides must be equal. So what methods are used to balance chemical equations? There are different kinds of methods that are used to balance chemical equations. These are the inspection method, least common multiple method, the algebraic method, oxidation number change method, and the half reaction method. Today we are going to see balancing chemical equation using oxidation number change method. I am going to focus on oxidation number change method to balance chemical equation. How can we balance chemical equations using oxidation number change methods? Let us see that. For redox reactions, in every redox reactions, you know that reduction and oxidations are taking place simultaneously. Where there is no oxidation, there is no reduction. So in redox reaction, the electrons lost during oxidation must be equal to the electrons gained during reduction. There are two ways to balance redox equations. One is using changes in oxidation number. The other one is using half reaction method. Now, as I've told you before, I'm going to focus on using changes in the oxidation number. Let us see how to use it. How to use oxidation number change method in balancing chemical equations. In this method, redox equation is balanced by comparing the increase and decrease in the oxidation numbers. We are going to compare increase and decrease on the oxidation number in balancing chemical equations using oxidation number change method. It can be balanced using the following steps or procedures, stepwise procedures. To balance chemical equations using oxidation number change, first should have to assign oxidation numbers to all elements in the reactions. Should have to identify atoms which are oxidized and reduced. Identify oxidized and reduced species. The third step that we use in balancing chemical equation using oxidation number change method, we are going to compute the number of electrons lost in the oxidation and again in the reduction. You should have to know how to calculate the oxidation number of atoms which are participated in chemical reactions that are given in chemical equations. So next, multiply one or both of these numbers by appropriate factors to make the electron lost equal the electrons gained, and use the factors as balancing the coefficients. The last step to balance chemical equation using this method, complete the balancing by inspection, adding states of matter. When states of matter should not be ignored when the product and the reactant part may be solid or gas or liquid. Should have to identify them whether they are solid, liquids, or gases. Let us see by this example. This chemical equation. Start with the balance equation. Silver nitrates reacts with copper, gives you copper nitrate and silver atom. Now, according to the steps in balancing chemical equations in redox reaction, the first step is assign oxidation number to each of the atoms in the equation and write the numbers above the atom. We are going to write the oxidation numbers on each species above the atoms. Let's say the oxidation number of silver in silver nitrate is +1. The oxidation number of nitrogen is +5. The oxidation number of oxygen is -2. These are the oxidation numbers. The oxidation number of copper, this copper is a free atom. The oxidation number of free atom is always 0 because there are equal number of electrons and protons. Electrons are neither gained or none lost in this case. But in copper nitrates, copper is oxidized. The oxidation number of copper is +2. The oxidation number of nitrogen here is the same to that of in the reactant side. There is no change in the oxidation number of nitrogen in the oxygen. Here, the oxidation number of silver atom is 0. Now, silver is reduced from +1 to 0. Now, we assigned all the oxidation numbers in each of atoms in this chemical equation. The second step, we are going to identify atoms that are oxidized and reduced. Which of these are oxidized and which of them are reduced? Let us identify. As you can see here, silver atom is being reduced because the oxidation number of silver is reduced or decreased from +1 to 0. So from +1 to 0, the copper atoms is being oxidized from 0 to +2, not +3, +2. It is oxidized to +2. And now we have identified the species that are oxidized and reduced. The next step is we are going to compute oxidation number change. We use, in this case, one bracketing line to connect the atoms that undergo oxidation and another line to connect that undergo reduction. So we connect by a bracket line. Now, copper is oxidized from 0 to +2. Oxidation +2. Then silver is reduced from +1 to 0. Now we compute the oxidation number change because there is only change in the oxidation number in copper and the silver in these chemical equations. As we identified, the next step, we are trying to make the total increase in the oxidation number equal to the total decrease in the oxidation number using the appropriate coefficients. As you know that the total number of electrons lost must be equal to the total number of electrons gained in chemical equations. So we are going to balance the number of electrons gained and the number of electrons lost on both sides of the equation. Let us see how to balance. So the least common multiple of 1 and the 2 is +2. Here, because here you have the oxidation number of copper is increased from 0 to +2. From 0 to +2, we multiply it by 1. And so the oxidation number increase should be multiplied by 1. The oxidation number decrease should be multiplied by 2. The oxidation number of silver is decreased from +1 to 0. So the total number of electrons lost in this case is 2. The total number of electrons lost in the copper is 2. The total number of electrons lost by silver must be 2. Now we balance the total number of electrons lost and gained. So now, the oxidation number increase should be multiplied by 1, while the oxidation decrease should be multiplied by 2. So that now we are going to see the total number of atoms on both sides of the equation. What coefficient should be written in front of symbols and formulas in both sides of the equation. 2 is placed in front of silver nitrate because here you have 2. The coefficient should be multiplied by 2. And the same thing is true on the other sides of the equation because this is to balance the total number of atoms of silver on the reactant side and on the product side. Let us check for the copper. Here you have 1 atom of copper and 1 atom of copper on the other side. Copper and the copper nitrate do not require a coefficient because it's already balanced. Now the equation is balanced. This is a simple way to balance redox equation. Finally, we are going to check whether the equation is balanced or not. So make sure that equation is balanced for both. Now the equation is balanced for both atoms and change. Now we balanced the equation now. Now everything is okay. The total number of atoms on both sides of the equation is equal. Another example. Balance the following equation by using oxidation number change method. Here is the equation is given. Potassium dichromate plus water plus sulfur gives you potassium hydroxide, chromium 3 oxide, and sulfur dioxide. What should we do? We should have to follow the steps that we used before. The first step is assigning oxidation numbers on each of the species in this chemical equation. So, what's the oxidation number of potassium? +1. What is the oxidation number of chromium here? Chromium, the oxidation number of chromium is +6 when you calculate the oxidation number of chromium, because the oxidation number of oxygen is -2. It's constant. The oxidation number of hydrogen here is +1, and the oxidation number of oxygen in water is -2. Sulfur, the oxidation number of sulfur is 0 because it's a free atom. And in this case, potassium has always oxidation number +1, and oxygen -2, hydrogen positive 1. Chromium in this case, plus 3, because the oxidation number of oxygen is negative 2. Because the total change on the oxidation number, the total addition of the oxidation, the electrons reduced or oxidized must be equal to 0. So chromium in this formula, in this equation, has positive 3. On the other side, sulfur, in sulfur dioxide, its oxidation number is positive 4. Oxygen, as usual, is negative 2. Now we assigned the oxidation number of each species in the chemical equation. The next step, now chromium reduced, sulfur is oxidized. Atoms, identifying the atoms that are reduced and oxidized. Chromium is oxidized. Chromium is reduced from positive 6 to positive 3. Sulfur is oxidized from 0 to positive 4. There is a change in the oxidation number of chromium and sulfur in this equation. The other atoms, there is no change on the other atoms in this equation. The only change on the oxidation state or oxidation number is on chromium and sulfur atoms. The next, we are going to make equal the number of electrons lost and the number of electrons gained. Now let's move to the next step. We are going to connect the atoms that changes in the oxidation numbers, because once we identified the reduced species and the oxidized species, now we are going to connect, as we say, connecting the atoms that changes in the oxidation number. In this equation, chromium, there is a change on the oxidation number on chromium and sulfur only. So we connect chromium atom on both sides of the equations. Chromium from positive 6 to positive 3. That is reduction. There is a change in oxidation number by 3. 3 electrons are gained by chromium. Sulfur from 0 to positive 4. It is oxidized. Now we identified the number of electrons lost and gained by the two atoms. So we balance the increase and decrease in the oxidation. How to balance the number of electrons gained or lost in these equations? For chromium, atoms must be reduced. The LCM method, we should have to multiply by 3. 4 minus 3 gives you 12, and 3 sulfur atoms must be oxidized. 3 times positive 4 gives you positive 12. Now, we should have to use these numbers as a coefficient. Put the coefficient 3, because in front of sulfur and sulfur dioxide. 2 in front of copper chromates and chromium 3 oxide. So we put 2 in front of this formula, 3 and 3, 2. Now we check. Now we should have to check the equation whether it's balanced or not. By what? If necessary, if the equation is not assumed to be not balanced, using the inspection method. Let us check. Here you have potassium, 4 atoms of potassium. Here you have only 1 atom of potassium. What about hydrogen? Let's check for hydrogen. Here you have 2 atoms of hydrogen. On the other side, we have only 1 atom of hydrogen. We should have to check for oxygen too. 2 times 7, 14. 14 plus 1, 15. 1, 2 times 3, 6. 6 plus 1, 7. 7 plus 6 is 13. Now, the equation is not still balanced. So, we should have to balance using the inspection method. Coefficient 4 in front of, we write the coefficient 4 in front of potassium oxide to balance what? Potassium. Because here you have 4 atoms of potassium on the reactant side. So we should have to write 4 in front of potassium hydroxide. Let's see. Coefficient 2. Coefficient 2 in front, we write 2 as a coefficient in front of water to balance hydrogen and oxygen. So let us check by writing the coefficients in front of these formulas. 4, 4. Now, here you have 4 oxygen, 4 hydrogen. Here you have 2, 14, 16. On the 16 atoms of oxygen on the reactant side. Let us check for the product side. 4 plus 6, 2 times 3 is 6, 4 plus 6, 10, 3 times 2, 16. Now, the total number of atoms on both sides of the equation is balanced. Now the equation is balanced. Don't forget that finally using to balance the inspection method. By counting the number of atoms on both sides of the equation. These are some examples that uses the oxidation number change methods to balance equations. Let us give you some activity. Try to balance the following equation using oxidation number methods. Here you have the equation. As we have tried to see before, you should have to change the oxidation number, and finally, you should have to use the inspection method. Please, students, try to balance this equation by yourself. Okay, that's all about the first lesson of part 4. Please try to exercise balancing chemical equations using oxidation number change methods in equations where there are oxidation and reactions are taking place in chemical reaction. Okay, let's come to the second lesson. The second lesson is limiting and excess reactants, determining the reactant that limits the product formed in the chemical reactions, and excess reactant that remains after the completion of the chemical reactions. How to identify or how to determine the limiting reactant in chemical reactions? Let us see that. How do we determine which reactant limits the amount of products that can form? Is it which reactant? Because in a chemical reaction, there are 2 or more reactants that may give another kinds of compounds or substance as a product. So which reactant from the given reactant, the chemical equation, which reactants that are used to determine the amount of products that can form in a chemical reactions. Chemical reaction involving, let us say chemical reaction involving 2 reactants only. So the reaction will stop when all of one reactant has been completely consumed. If one of the reactant is completely consumed, the reaction will stop. The reaction will stop. It is the reactant that determines the product that will be formed as the final stage of the reaction. So what is the limiting reactant after that? Used up in a reaction. Which is completely used up in a reaction is what you call limiting reactant. It limits or determines the amount of products that can be formed. What about excess reactant? What reactant is said to be excess? It is a reactant present in quantities greater than necessary to react with the quantity of the limiting reactant. The excess reactant is the reactant that remains unreacted in the chemical reaction. This excess reactant does not determine the products that will form. The reactant that determine the product that will form in the chemical reaction is called limiting reactant. The product is based on the limiting reactant, because after limiting reactant is used up, the reaction will stop. The remaining reactant will be excess reactant. Excess reactant. Let us see how to determine how to identify limiting and excess reactant. Let us see an analogy. Let us use some analogy that is connected to your daily life. Limiting reactant analogy using the production of or the preparation of sandwich, cheese sandwich. Let us say you have bread and cheese. Bread plus cheese will give you cheese melt or sandwich. To prepare a sandwich, you have to have piece of bread and one slice of cheese will give you what? One sandwich. Let us use this formula, this analogy to understand the limiting and the excess reactant in chemical reactions. So you are given 100 bread and you have 30 slices of cheese. How many sandwiches can you prepare from 100 pieces of bread and 30 slices of cheese? Let me ask you a question. Here you have, you may guess the number of sandwiches that might be prepared from this amount of bread and slice of cheeses. You can say 130 sandwiches, 100 sandwiches, 90 sandwiches, 60 sandwiches, 30 sandwiches. You may say not enough information is given. What is your guess here? Which guesses are the correctly guessed? Let 30 sandwiches. You can only prepare 30 sandwiches according to the ratio of the bread to that of the cheese. Two pieces of bread combining with one slice of cheese will give you a sandwich. So you have 100 bread and 30 slices of cheese. Which one of this reactant? Is it bread or the slices of cheese that determines the amount of sandwich that can be produced from this sandwich and bread and cheese? So you can only produce 30 sandwiches, which remains excess, which determines or which limits the amount of sandwich that can be produced in this case. Let us question. The number of sandwiches is limited by the number of slices of cheese. Cheese is the limiting reactant and the bread remains in excess. So because you have only 30 slices of cheese, you can only produce 30 sandwiches. 30 sandwiches, one slice of cheese needs 2 bread, or you use only 60 bread. 60 bread with that of 30 slices of cheese will give you only 30 sandwiches. How many pieces of bread are left in excess? So number of sandwiches limited by the number of cheese. Cheese is the limiting reactant and bread is excess reactant. Excess reactant. Assuming that this is a chemical reaction. Assuming that. So another analogy to make you more clear about the determination of limiting reactant and excess reactant. Consider this analogy, the construction of car. Here you have car bodies. How many car bodies are there here? 8 car bodies. This car bodies needs tires. Each of the car needs 4 tires to construct one car. Here you have 14 tires. 14 tires. 14 tires. 8 cars are produced or constructed. Which of these car bodies or parts of the cars are the limiting parts of the car that limits the number of cars that can be constructed? Is it the car bodies or the tires? Here you have 48 tires and 8 car bodies only, which limits the number of cars that can be constructed. So 1 car body plus 4 tires will give you 1 complete car. Assume this is a chemical reaction or a chemical equation. Car body plus 4 tire gives you 1 complete car. So which one is excess and which one is limiting? What is the limiting part and what are the excess parts? Now, 1 car uses 4 tires. 4 plus 8, 4 times 8 will give you 32 cars. 32 tires are used, but here you have 48 tires. How many tires are remained in excess? What is the limiting part and what is the excess part of the car body? The car body is the limiting part because it will be completely used up. There is no car bodies that left behind because we have excess tires. The number of cars may depend on the number of car bodies available. So the number of car bodies available limits the number of cars that can be constructed. If there were 4 more car bodies, then another car could have been made with the remaining tires. Around 16 tires are remained, so the tires are excess. The car bodies are the limiting part for the formation of the cars. Let's come to the reality of the chemical reactions. Here you have 8 carbon atoms, see. To produce methane, there must be hydrogen molecules. These are the hydrogen molecules, total representation of hydrogen molecules. Here you have 24 hydrogen molecules and 8 carbon atoms. How many molecules of methane can be produced from these two? From 8 carbon atoms and 24 hydrogen molecules. How many methane can be formed or produced? Let us see. 1 carbon atom needs 4 hydrogen atoms. 4 hydrogen atoms. How many hydrogen atoms are here? 24 hydrogen molecules, 48 hydrogen atoms are there. So you can only produce 1, 2, 3, 4, 5, 6, 8 methane molecules. How many hydrogens are used up here? How many hydrogen atoms are used up? From 48 atoms of hydrogen. So you have 8 methane. Which one is the limiting reactant and which one is the excess reactant in this reaction? The production of methane, because of the reaction between the hydrogen molecules and carbon atoms. The number of carbon atoms are given, hydrogen molecules are there. What is remained in excess? What is totally used up? So which one is the limiting reactant in this reaction? So plus 16 hydrogen atoms excess. Because in this case, 8 times 4, only 32 atoms of hydrogen are used in the formation of methane. But here you have in the reactant side, the 48 atoms of hydrogen. So 16 hydrogen atoms remains in excess. So in this case, hydrogen is the excess reactant. What limits the amount of methane produced? Plus 8 hydrogen molecules in excess. That means 16 atoms of hydrogen. So this is the balanced chemical equations. So the limiting reactant in the previous reaction is carbon atoms. Excess reactants are the hydrogen molecules. Hydrogen molecules are remained in excess. So the amount of methane produced will depend on the number of hot carbon atoms given this reaction. Let's see another example. This is to make more clear for you in determination of limiting reactant and excess reactant. Here we have in container, this container, we have hydrogen and nitrogen molecules. This is a vessel. This one represents hydrogen molecule, the other one represents nitrogen molecule. So the reaction between hydrogen and nitrogen will give you ammonia gas. Before the reaction and after the reaction. This ammonia represents the ammonia molecule. How many molecules of hydrogen are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we have 1, 2, 3, 4, 5 molecules of nitrogen. Or you can say moles of nitrogen or moles of hydrogen. So let's see the reaction between hydrogen and nitrogen. Which one of these are the limiting reactant and which one of these are the excess reactants? This is before the reaction and after the reaction. So all the hydrogen in this case, because according to the balanced chemical equation, here is the chemical equation. 1 mole of nitrogen will react with 3 moles of hydrogen to give 2 moles of ammonia, or 2 molecules of ammonia. 1 molecule reacts with 3 molecules to give you 2 molecules of ammonia. So for each molecule of nitrogen, there must be 3 molecules of hydrogen. 3 molecules of hydrogen. For 1 molecule of ammonia, there must be 3 molecules of hydrogen. 3 molecules of hydrogen, 3 molecules of hydrogen, 3 molecules of hydrogen, 3 molecules of hydrogen. Is there excess reactant in this case? Which one is excess reactant and which one is limiting reactant? This shows before the reaction, after the reaction, ammonia is produced. There is no any reactant that remains in excess after the reaction. So all the hydrogen and the nitrogen atoms combine. So both the nitrogen and hydrogen ions are the reactants that limit the formation of ammonia in this case. No excess reactant. Let's go to the next. Here you have, in this container, 1, 2, 3, 4, 5 molecules of nitrogen. How many molecules of hydrogen do we have here? 1, 2, 3, 4, 5, 6, 7, 8. We have only 8 molecules of hydrogen in this vessel. Before the reaction. According to the balanced chemical equation, there must be 3 molecules of hydrogen for 1 molecule of nitrogen. So if proportionally combined, look at this one. These are molecules of nitrogen. After the reaction, what remains in excess? Which molecules are remained in excess? Is it hydrogen or nitrogen? Here you have excess molecules of nitrogen. Which of these reactants will determine or limit the amount of ammonia produced? This is a balanced. 1 molecule of nitrogen must combine with 3 molecules of hydrogen, according to the figure that you are seeing here. So before the reaction, after the reaction, nitrogen molecules are remain because of the scarcity of hydrogen. So nitrogen is excess reactant hydrogen is the limiting reactant because all hydrogen molecules are used up in the formation of ammonia. So the one that used up completely is said to be the limiting reactant. In this reaction, it is hydrogen that limits the amount of ammonia produced. So hydrogen is a limiting reactant. The limiting reactant determines the amount of the product. So hydrogen is a limiting reactant, as well as nitrogen is excess reactant. So now consider the chemical reactions burning of hydrogen in oxygen. Another example. When hydrogen combines with oxygen producing water. So suppose you put 1 mole of hydrogen and 1 mole of oxygen into a reaction vessel. 1 mole of hydrogen and 1 mole of, let us say, 1 mole of hydrogen and 1 mole of oxygen is put together in the reaction vessel. So in this case, hydrogen reacts with oxygen, or hydrogen is burned in oxygen, producing hydrogen molecule. And in this ratio, the reaction between oxygen and hydrogen, 2 moles of hydrogen is completely reacted to that of 1 mole of oxygen, producing 2 moles of hydrogen. So for each mole of oxygen, there must be 2 moles of hydrogen for the reaction to be complete. Suppose you put 1 mole of hydrogen and 1 mole of oxygen into a reaction vessel. How many moles of water will be produced? How many moles of water will be produced? If you have 1 mole of oxygen and 1 mole of hydrogen in the same vessel, the reaction vessel. Let us say, you should have to calculate. First, you know that 2 moles of hydrogen produce 2 moles of water. And 1 mole of oxygen produces 2 moles of water from the given balanced chemical equations. So calculate the number of moles of hydrogen water that could be produced, or that could produce from each quantity of the reactant. We should have to calculate using both reactant the amount of water that will produce. So using hydrogen. Now I've said that we have 1 mole of hydrogen in the reaction vessel and 1 mole of oxygen. Using calculating the amount of water that will produce in the reaction vessel using 1 mole of hydrogen, according to the stoichiometric method of calculating the amount of products produced and the amount of reactant needed to produce a product. 1 mole of hydrogen times 2 mole of water. Let us make it clear. Okay, here you have hydrogen plus oxygen will give us water molecule. Let us balance the equation. Here you have 1 molecule of oxygen and 2 atoms of oxygen. To balance the number of atoms of oxygen on both sides of the equation, we should have to write 2 as a coefficient in front of water molecule. Here you have 4 atoms of hydrogen, but we have only 2 atoms of hydrogen, so we should have to make the balance. Now we balance it. From the balanced chemical equations, 2 mole, here you have 1 mole. 2 mole will give us 2 mole of water. But we have 1 mole. How many moles of water will be obtained when 1 mole of oxygen is used? So let us make 1 mole. 2 mole will give us 2 mole. 1 mole will give us 2 moles. So 1 mole of hydrogen molecule times 2 mole of water molecule will give you 2 moles of hydrogen times X mole of water. X mole of water will be obtained. What is the value of X in this case? 1 mole of hydrogen plus 2 mole of water over 2 moles of hydrogen. Now we can calculate the amount of water molecule that will be produced, the number of mole of water molecules that can be produced if 1 mole of hydrogen is used. So as you give, X mole of hydrogen will be, X mole of water will give us 1 mole of hydrogen. 1 mole of water, 1 mole of water. What about in the case of oxygen? The same thing is true. We have 1 mole of oxygen in the reaction vessel. 1 mole of oxygen with enough amount of hydrogen molecule will give us 2 moles of water. So in the case of hydrogen, X mole of water will give you 1 mole of oxygen times 2 mole of water molecule over 1 mole of oxygen. So X mole of water will have 2 moles of water. In this case we have 1 mole of water. Is it oxygen or hydrogen that limits the amount of water molecule produced in this reaction? Which one is the limiting reactant and which one is excess reactant? The limiting reactant, the reactant that gives us the low amount of products, less amount of product. Less amount of product is obtained if you use 1 mole of hydrogen. So we cannot obtain this much amount of water from 1 mole of hydrogen, but we can obtain if we used excess amount of hydrogen, we can get 2 moles of water. So which one is a limiting reactant? Which one is the excess reactant? Now, hydrogen is the limiting reactant, oxygen is the excess reactant. Let us see. The reactant that limits the amount of product produced, the amount of water produced in this reaction, the reaction between hydrogen and oxygen. In case of hydrogen, 1 mole of oxygen produced will give us 2 mole of water, as we have calculated. Which is the limiting reactant and which one is the excess reactant? So hydrogen yields the least amount of products. That gives the reactant that gives the least amount of product is the limiting reactant. Oxygen is the excess reactant because oxygen gives the high amount of the product that cannot be produced actually in reality. So when an equal number of moles of hydrogen and the oxygens are reacted according to the equation, we'll have all of the hydrogen completely react, whereas only half of the oxygen is consumed. So half of the oxygen is remain in excess because there's no enough hydrogen. So look at this picture. This is hydrogen, oxygen. In the same vessel, which molecules remain in excess? Oxygen molecules are remain. Half of the oxygen molecules are remain in excess. So in this case, oxygen is excess reactant and hydrogen is the limiting reactant that limits. And what type of steps to calculate the amount of reactant needed to react with other reactant? Steps for determination of the limiting reactant. Let you have A plus B, 2 reactants, will give you some product. Let's assume that. Calculate the amount of the reactant B needed to react with the other reactant A. So we have A and the B are reactant. How can you determine the limiting reactant? Compare calculated amount of B to the actual amount of B that's given. If calculated B is equal to the actual B, if calculated B is equal to the actual B, there is no limiting reactant. both A and B will react completely. If calculated B, we are going to calculate for the amount of B. If calculated B is greater than actual B, B is the limiting reactant. If calculated B is greater than the actual B, B is the limiting reactant. Only B will react completely. If calculated B is less than actual B, A is the limiting reactant. Only A will react completely. This is how to determine the limiting reactant. We should have to calculate for both reactants, for all the reactant in chemical reactions. The actual reactant and the calculated reactant. You compare the actual reactant and the calculated reactant to determine the limiting reactant. The balanced equation, let us activity. The balanced equation for the reaction of phosphorus and oxygen gas to form phosphorus pentoxide is this one. This is chemical equation for the reaction between phosphorus and oxygen. Give us phosphorus pentoxide. What is the limiting reactant? When each of the following sets of quantities of the reactant is mixed. If 0.5 mole of phosphorus is mixed with that of 5 mole of oxygen. If 0.2 mole of phosphorus is mixed to that of 1 mole of oxygen. If 0.25 mole of phosphorus mixed with that of 0.75 mole of oxygen. Please try to find out the limiting reactant in each case. In each case. In A, each mole of phosphorus requires 5 mole of oxygen. So 0.5 mole of phosphorus requires. 0.5 mole of phosphorus requires. So look at this. You have 0.5 mole, 5 mole. According to the balanced chemical equation, 2.5 mole of oxygen is required. The amount of oxygen is more than the amount required. The calculated amount of oxygen, 2.5 mole oxygen. The amount of oxygen present is more than the amount required. So in this case, phosphorus is the limiting reactant and oxygen is present in excess. In excess. 2.5 mole of oxygen remains unreacted because we have excess amount of oxygen. For this case, each mole of phosphorus requires 5 mole of oxygen according to the balanced chemical equation. So 0.2 mole phosphorus requires. So 0.2 mole phosphorus will require 1 mole of oxygen. So since this is the amount of oxygen present, there is no limiting reactant. Both reactants are consumed completely. In this case, there is no limiting reactant and no excess reactant. The same thing is true for the others, for the second or C. So you can practice using taking different types of exercise to determine the limiting and excess reactant in the given chemical reactions. This is all about the way to determine the limiting and excess reactants in the chemical reaction. The next topic, the next lesson is identifying the difference between suspensions, solutions, and colloids. What are solutions? What are suspensions? What are colloids? What are the difference between the three? And what are the similarities among these? All are mixtures. What type of mixtures are they? What makes them to be different from one another? Let us see. These three kinds of mixtures. Suspensions, solutions, and colloids. You know that mixtures are two types: homogeneous and heterogeneous mixtures. You can also classify mixtures into three: suspensions, colloids, and solutions. All these are mixtures. You can classify these mixtures into two groups: in heterogeneous and homogeneous. Which one is homogeneous and which one is heterogeneous among these mixtures? Let us see them one by one. What is suspension? What's the difference between suspension, colloid, and solution? What is suspension? Suspension is a heterogeneous mixture in which the solid particles are spread throughout the liquid without dissolving in it. There are some solid particles. If there are some solid particles remaining undissolved, suspended in a solvent, that kind of mixture is what you call suspension. Suspension. So the solid particles are visible to the naked eye. You can see the solid particles suspended in a liquid. So if solid particles are seen by using the naked eye, that kind of mixture is said to be suspension. So they remain suspended throughout the bulk of the medium. What are the examples? Examples of suspensions that are connected to your daily life experience. Examples of suspension: mud suspended in water, the mixture of soil and water. You can see the suspended solid particles in water. Mixture of chalk, and water is another example of suspension. Paints, water-based paints. Water-based paints are example of suspension. Suspensions, what is solution? What is solution? Now, we have already defined suspension. I've already defined suspension. Suspension is a mixture in which undissolved solid particles suspended in the bulk of the liquid. So, solution is another kind of mixture. What kind of mixture is it? It is homogeneous mixture. Solid dissolved in a solvent. So, what is the property? What it makes different from that of suspension? A solution has a single uniform phase, has no visible boundaries. You cannot see the solid particles in solutions. So the components are individual atoms, ions, or molecules, distributed throughout the solutions. The molecules, the ions, or the atoms are uniformly distributed throughout the solvent. So you cannot see ions, molecules, or atoms. So there is no limited boundaries or single uniform phase in case of solution. So this is why you call solution is homogeneous. The components do not separate, neither coagulate upon standing, nor by filtration. You cannot separate solids from in the solution by filtration, by coagulation, or by putting them standing, making them stable. So types of solutions, you know that there are different types of solutions: gas solutions, liquid solutions, and solid solutions. Now, here is an example of gaseous solution, which contains oxygen, nitrogen, and smaller amounts of other gases. So, air is one type of solution. For example, carbon dioxide gas in water, acetone in water. Brine solution are examples of liquid solutions. Liquid solutions. What about solid solution? Alloys. Alloys, the mixture of metals. Gold, silver alloys, dental filling, liquid mercury, solid silver solution, wax, hydrogen, vanadium, gas in solid used for hydrogen storage, are examples of solid solutions. Our aim is not to define what is solid solution, what is liquid solution, and what is gas solutions. Now we are going to differentiate the three types of mixtures: solutions, suspensions, and the colloid. What are colloids? Now we define what a solution is and the suspension. What's colloids, or what are colloids? Colloids are a heterogeneous mixture that has particles ranging between 1 and 1,000 nanometer in diameter. The size of particles of colloids in the mixture is from 1 nanometer to 1,000 nanometer in diameter. It is heterogeneous. Example. You cannot see the particles in colloids. For example, blood is one example. Contains red and white blood cells. You cannot identify the red blood cells and the white blood cells in a blood using your naked eyes. But it is an example of fog and the smoke. Fog and the smoke are another examples of colloids, which are liquid droplets or solid particles dispersed throughout a gas. And emulsions, liquid in liquid, consists of liquid droplets dispersed throughout another liquid. For example, particles of butter, fats are dispersed through homogenized milk. Now you know that milk is a mixture. What type of mixture is it? Heterogeneous mixture. A solid in liquid consists of a solid particles dispersed in it. These are some examples. Yes. Let us see examples that are connected to your daily life experience. Let us see some examples of colloids in daily life. Form is one example of colloid. Milk, as I have told you that. Smoke, solid particles dispersed throughout the gas. Detergents, gel, blood, as I have told you that. An example of colloids. And paint, another type of paint. It's not water-based paint. Cosmetics, these all are examples of colloids. Examples of colloids. There are two phases in colloidal solutions. What are the two phases in solutions? What are the two components in solutions? Solid and solvent. What about in case of colloids? The dispersion phase and the dispersion medium. What is dispersion phase and what is the dispersion medium? The component present in a smaller proportion is dispersion phase. The one present in greater proportion is the dispersion medium. What about in the case of solution? Which of the component is present in a smaller in a smaller proportion, and which one is present in the greater proportion? The one that present in greater proportion is said to be solvent. The one that is in a smaller proportion is said to be solutes in the case of solutions. In the case of colloids, we have dispersive phase and dispersion medium. Dispersion medium. This dispersive phase is that what in case of solution we say that solutes. This is dispersion medium, dispersive phase, dispersed throughout the dispersion medium will give us mixture. That mixture is said to be colloid. Colloid. So particles in colloid, particles do not separate on keeping. The presence of colloidal particles is easily detected with the aid of light beam. You cannot detect using naked eye, but you can see when you use a light beam. So it scatters the beam of light passing through it. So the light beam is not visible as it passes through the true solution, but in the case of colloids, it is clearly visible when it passes through a colloid. When you pass light through a solution, the light cannot be seen when it is passed through the solution, but you can see the light when it is passed through the colloids. So the dispersion of the beam of light by colloidal particle is called what you call the Tyndall effects. The Tyndall effect makes the path of the light beam visible. This effect makes the light path in colloid to be visible. This is called what you call Tyndall effect. Colloids scatter the light, making the beam visible. As I've said, solution do not scatter light. Tyndall effect in suspensions disappear as particles settle down. Let us see the difference between the three. Flashlight is a solution. When the light passes through the solution, the light cannot be visible or cannot be seen. There's no, when it passes into colloids, the light is visible. In the case of suspension, the reflection of light is absorbed. So you can identify whether the mixture is a solid, solution, suspension, and colloid should have to pass light, pass through it. So what are the difference between the particle size? Salt solution is it? The particle size of the solid is less than 1 nanometer. In the case of colloids, we take milk, the particle size is from 1 nanometer to 1,000 nanometer. In the case of suspension, the particle size of the solutes in the solution is very larger. Let us see some very short animated videos that makes us more clear about suspension, colloids, and the solution. Okay. Okay. In this case, this is an example of colloids. When the flashlight or light is made to pass through this colloid, and the light is scattered, you can see the suspended or dispersed medium, the colloids, in this mixture. This is the suspension. It reflects the light that passes through it. But you cannot see, or you'll see, the light, in this case, the light is simply pass through it. You cannot see light here. So this is the difference. This video shows the difference between suspension, colloids, and the solution. In the solution, the beam of light is not visible. In this case, visible. The light is visible. In this case, it reflects the light. So the video shows the difference between will a light ray less pass through and scattering and reflecting. So you can identify the kind of mixture, whether it is colloid, suspension, and solution, by passing the light beam through the mixture. Let us summarize the difference between the three: the property, the solution, the suspension, and the colloids. The nature of the solution is homogeneous, suspension and colloids are heterogeneous. The particle size of the solutes in solution is less than 1 nanometer, in suspension greater than 1,000 nanometer, in the case of colloids in between 1 nanometer and 1,000 nanometer. Sedimentation. Solutes that do not settle down. in case of solution. In case of suspension, settle on standing. The solid will precipitate. Colloids does not settle. There is no settlement in the case of colloid. Diffusion. Solid diffuse quickly in suspension, unable to diffuse. Colloids diffuse slowly. Visibility of the solid. Particles invisible in the case of solution. In the case of suspension, particles are visible. What about in the case of colloids? Particles scatter light. You can see when through the light. Filterability. Pass easily through filter paper. Solid cannot be filtered out from the solution. In suspension, unable to pass through filter paper. You can separate solids from the solvent in the case, and mixtures, the two types of mixtures, liquids and the solid suspended particles using a filter paper. And in the case of colloids, the particles pass through filter paper because they are small in size. Appearance, clear and transparent. What solution? Suspensions are opaque. Opaque. Does not pass light through it. It reflects the light. What about colloids? Colloids are translucent. Partially, the light is partially passing through the mixture. So, let us see some activities or some questions. These are what you have already seen. To remind you that, try to classify the following mixtures into suspension, solution, and colloids. Here you have given milk, butter, gelatin, chalk in water, salt in water, acetic acid in water, flour in water, dust particles in air, fog, air, blade. Please try to classify these kinds of mixtures into suspensions, solution, and colloids. Try to identify which mixtures are suspension, which are solution, and which are colloids. This is left for you. What are the similarities and differences among of solutions, suspensions, and the colloids? The similarities, all of them are mixtures. That's all about solutions, suspensions, and the colloids. I hope that you have the concept of solutions, colloids, and suspensions. So you can identify the three types of mixtures using their physical properties. That's all about these mixtures. And the next will be the way solution forms, the process of formation of solution. This is lesson 4. What are the components of solutions? The components of solutions are solutes and solvents. Now we are going to see how solutes are dispersed throughout the solvent, how they form solution. Let us say the process. You know that gas mix freely. Why? Because the molecules are widely spaced. There is large space between the molecules of gases. They can easily mix together. So gas mix freely. The formation of liquid and solid solutions requires overcoming the solute, the solvent interparticle force of attraction before the mixing step. So solution to be formed. Then what's required? Overcoming of intermolecular interaction or interparticle forces of attraction between solid and solvent. Okay, in liquids and solids, molecules are held together by intermolecular attractions. What are intermolecular attractions? The attraction between two molecules. The attraction between the two molecules, what you call intermolecular attraction. And when one substance dissolves in another substance, particles of the solid disperse throughout the solvent. So solid particles now occupy the positions of that are normally taken by the solvent molecules. Solutes takes the position of that's already taken by the solvent, and they mix together. What kind of solute and the solvents form solutions? What are the properties of the solute and the solvent for the solution to be formed between the solute and the solvent? So a good rule of thumb predicting the solubility, that is like dissolves like. What does it mean like dissolves like? That means substance with similar intermolecular forces form solutions, and substance with different intermolecular force do not dissolve, do not form a solution. There must be similar intermolecular force of attraction between the solute and the solvent for the solution to be formed. So solid particles replace a solvent molecule depending on relative strength of three interactions. What are the three interactions? Solvent-solvent interaction, solid-solid interaction, and solvent-solid interaction. So this solid particle replace solvent molecule depends on this, the strength of the three types of interactions. So a solution to be formed, it depends on these interactions. Okay, let us see the following steps. A solution is formed. The solution process involves three basic steps. The three basic steps: area of the solvent, and step one. And in the first step, breaking of the solvent intermolecular forces. The intermolecular force between the solvent molecule should be broken up. So, and the solvent molecule expanded. That's giving space for the solute that comes, that's going to dissolve in a solvent. So, separation of solvent molecules, in this step, energy is absorbed, heat is absorbed. For that case, the process is endothermic. The process is endothermic. It needs some amount of energy to be expanded, to give space for the solid particles. And solute, the second step, solute, just like that of the solvent, the solute, the interparticle force should be broken for the solid too. So there's the expansion of the solids. Now they are ready to mix together. So the separation of solid molecules needs energy, entropy. Heat is absorbed, or energy. In this case too, this process is also endothermic. The process is to endothermic. The last step is formation of a solution, or mixing or dissolving solid particles into solvent. Now they are mixed. This is a solution, mixed. And this step, in the formation of solid-solvent interactions, some amount of energy must be released because they should come together. And the process is what we call exothermic in this case. In the third step, exothermic for the solution to form here. So this is the three basic steps in which solutions are formed. And the total entropy change, heat of solution is equal to energy, heat change in the first step, change in the second step, heat change in the third steps. So the main interactions that affects the solution of solids in solvent is, as I've said, that there are three types of interactions: solvent-solvent interaction, solid-solid interaction, and solvent-solid interaction. Solid-solvent interaction must overcome solid-solid interaction and solvent-solvent interaction to the solution to be formed. So the main interactions that affect the dissolution of a solid in a solvent is follows this: weak solute-solute interaction favors solubility. If there is weak solute-solute interaction, the interaction between the solid particles can be overcome by solvent-solute interaction. So in this case, solubility is favored for the solubility to be favored. The second one, weak solvent-solvent interaction favors solubility. If there is weak solvent-solvent interaction, they can easily be overcome by solid-solvent interaction. Strong solvent-solid attractions favor solubility. If there is a strong solvent-solid interactions, the solution can be formed. Solution can be formed. So, if these conditions are fulfilled, solubility will be favored. You can form, solution can be formed. So, the intermolecular or interionic attractions among solid particles in the pure solid must be overcome to dissolve the solutes. So, the intermolecular or interionic attractions among solid particles in the pure solvent must be overcome. The same thing is true. The solvent in molecular interaction should be overcome. So, what is like dissolve like? Like dissolve like? Like dissolve like? Polar solvent dissolve polar solute, sometimes ionic. Some ionic substance can be dissolved in polar solvent, not all. Non-polar solvent dissolve non-polar, because we'll see how non-polar solvent dissolves non-polar solvent. Polar solvent dissolves polar solvents. That means like dissolves like. The useful rule of term like dissolve like says that substance with similar types of intermolecular force dissolves in each other. That's what I've already said before. And when the interparticle forces within the solids are similar to those within the solvent, the force replaces each other, then a solution forms. Similar intermolecular attraction force will produce solution. And what intermolecular forces are involved in the formation of solution? What types of intermolecular forces are involved in the formation of the solution? So, the covalent bonds are called intramolecular force. What's the difference between intramolecular force and intermolecular force? That is a force within a molecule. The force within a molecule is what we call intramolecular force. The force of attraction between the molecules, we call that intermolecular force of attraction. So, intermolecular forces are also called non-covalent interaction. The first one is covalent interaction. This one is non-covalent interaction. So, they are attractive or repulsive force between the neighboring molecules. If there is attracting between the neighboring molecules, we say that force of attraction is intermolecular force of attraction. Let us see example. Look at this picture, this figure. Chlorine, hydrogen chloride molecule. This is hydrogen chloride molecule. The bond between chlorine and hydrogen is a covalent bond. Covalent bond. The force of attraction between chlorine and the hydrogen is intramolecular force of attraction. This is strong force of attraction. This is the covalent bonds are, as I said, called intramolecular forces. This force is what we call intermolecular force. The attraction hydrogen and the chlorine. The bond between hydrogen and the chlorine is covalent bond. The attraction between chlorine and hydrogen atom is called intramolecular force of attraction. There is also another attraction between the molecules of hydrogen chloride. This is a covalent bond. The attraction force between the two molecules is called intramolecular force of attraction. This is weaker than that of intramolecular force of attraction. Intramolecular force of attraction is very strong. So, this is a difference between intramolecular force of attraction and intermolecular force of attraction. So, is force of attraction. What kind of attraction is involved in the formation of solution? It is intermolecular force of attraction, not intramolecular force of attraction. So these are the force of attractions, intermolecular force of attraction between the molecules or ionic particles, and the polar molecules are maybe dipole-dipole interaction, dipole-induced dipole interaction, dispersion force or London force, ion-dipole interaction, ion-induced dipole interaction, hydrogen bonding. Hydrogen bonding. Hydrogen bonding is not a covalent bond. It's not a bond. It is a force of attraction between between two molecules. So the relative strength of this force in order of weakest to strongest is, which one is the strongest force of attraction and the weakest force of attraction? The order is dispersion force is weaker than dipole-induced dipole. Dipole-induced dipole interaction is weaker than dipole-dipole interaction. Dipole-dipole interaction is weaker than hydrogen bonding. Hydrogen bonding is weaker than ion-dipole bond. Ion-dipole bond interactions. These are the types of intermolecular force of attraction that can be involved in the formation of solution. So let us see the involvement of these interactions in the formation of don't forget that like dissolves like. What does it mean? I saw polar dissolves in polar, non-polar dissolves in non-polar. And some ionic substance can be dissolved in the polar solvent. Dipole-dipole force. What's the dipole-dipole force? What type of interaction what type of interaction here is it? Electrostatic force of attraction. This is the electrostatic force of attraction between the molecules, polar molecules. For example, let us see this figure. Polar molecules have dipole moment. Dipole moment greater than 0. Have partial negative charge on one end and partial positive charge on the other end. There is a difference between the electron distribution in between the atoms in a molecule. So there is attraction between polar molecules, I say that, polar molecules. This is electrostatic attraction force between polar molecules. Negative end of the one molecule attracts the positive end of the other molecule. So there is force of attraction. This force of attraction is electrostatic force of attraction. This force of attraction between the two molecules is what we call dipole-dipole force. Dipole-dipole force. For example, polar molecules dissolves in polar liquids. Like dissolves like. So solubility of hydrogen bromide in water. Water is polar molecule. Water is a polar molecule. Now, you know the structure of water. This is the structure of water molecule. Here you have, there is a greater electronegative difference between hydrogen and oxygen. So oxygen is more electronegative than that of hydrogen and highly attracted to oxygen because oxygen is more electronegative element. And much of the electron density is accumulated on the oxygen, on the central atom oxygen atom. So oxygen atom attains partial negative charge. This attains partial positive charge, thus partial positive charge. What about hydrogen bromide? Hydrogen bromide is also polar molecule. Bromine is, the electronegativity of bromine is greater than that of hydrogen. In this case, this is partially positive, partial negative, partial positive. there is dipole attraction between the two molecules. The negative end of hydrogen bromide molecule attracts the positive end of water molecule to that of the hydrogen. There is force of attraction between, electrostatic force of attraction between water molecule and the hydrogen bromide molecule. The attraction between the two molecules is what we call dipole force. So the solubility of hydrogen bromide in water. So hydrogen bromide is soluble, it can be dissolved in water because there is force of attraction, dipole force of attraction between the solvent and the solute, the two molecules. And next, dipole-induced dipole interaction. What type of interaction is it? It arises when a polar molecule distorts the electron cloud of a non-polar molecule. It is the intermolecular attraction between the dipole and non-polar molecule. How non-polar molecules are attracted by the polar molecule. There is, for example, the solubility in water of atmospheric oxygen, nitrogen, and noble gas. You know, so oxygen is dissolved in water. How oxygen dissolves in water? How nitrogen dissolves in water? Because oxygen is non-polar, water is polar. What kind of interaction is there between the two molecules? So let us see one example. This is polar molecule, the other one is non-polar molecule. They are far apart from each other. There is no interaction. But when they come closer together, the electron cloud of the non-polar molecules are distorted and induced. When they come closer, electrons are moving to one side and attaining temporary charge. In this case, the attraction between dipole and the non-polar molecules is happening. For example, here you have oxygen molecule, isolated oxygen molecule, non-polar, induced dipole oxygen molecule. If oxygen is induced, induced dipole attraction is happening between this is water molecule. Water molecule have permanent dipole. This has a temporary dipole because of the distortion of the electron clouds on the oxygen atom. So it attains temporary charge. For that matter, oxygen dissolves in water. Such kinds of interaction is called dipole-induced dipole interaction. Dipole interaction. You can see this one coming together and in distortion of the electron cloud. In this case, the oxygen atom attains temporary charge and the force of attraction between the two will happen. Now, in this case, oxygen can be dissolved in water. These types of interaction is said to be dipole-induced dipole. What about dispersion force? This is London force. Weak attractive intermolecular force between two atoms or two non-polar molecules due to temporary dipole created by electrons motion. The interaction between non-polar. Weak intermolecular force of attraction is what we call dispersion force. Dispersion force. Where there is an equal distribution of electrons in the molecule. Temporary dipoles are created by electrons motion due to the movement of electrons from one side to another side. So the attractive force will happen between the two molecules because of the temporary dipoles. This kinds of dispersion force are called London force. For example, take this one, helium atom. The helium atom has two electrons, another helium atom. When one of the electrons of helium is moved to one direction, the direction in which electrons are moving attains a negative charge, the other one attains positive charge, and there is a formation of temporary charges on two atoms, so that temporary electrostatic force of attraction is created. So this types of force of attraction is what you call dispersion force. This is what you call the momentary shift in electron density attaining temporary dipole. These forces are present in all molecules, whether they are nonpolar or polar. Whether they are nonpolar or impolar. The other one is ion dipole forces, ion-induced dipole force. This is polarization. Polarization. When the ion and the nonpolar molecules get closer, the nonpolar molecules get polarized. It becomes polarized. How? When an ion's charge distorts the electron cloud of nearby nonpolar molecules. When ions distort the electron clouds of nonpolar molecules. So again, the nonpolar molecule is polarized. What polarizability? This polarizability is the tendency of, or the extent to which the electron cloud of an atom or a molecule can be distorted by an external electric charge. So ions have charged particle. These ions can distort when the ions and nonpolar molecules are coming together. The electron clouds of nonpolar is distorted, and the attraction between ion and induced dipole molecules are. Look at this. These are ion A and ion B. These are nonpolar molecules. When these nonpolar molecules get closer to each other, the electron clouds of this nonpolar molecule is distorted, or polarization is taking place. Then it attains temporary charge. In this case, the electron shifts to one side and attaining a negative charge, and the other side will attain the positive charge. There is intermolecular force of interaction is taking place. Intermolecular force of attraction. Such kinds of intermolecular force of attraction is said to be ion-induced dipole force. The best examples for this solution is ion-induced dipole force initiates the binding of iron ion in hemoglobin to an oxygen molecule entering a red blood cell. There are oxygen in the red blood cells. What makes oxygen to be dissolved in a blood? The interaction between ion and oxygen due to ion-induced dipole force. This is iron ion in hemoglobin to an oxygen molecule entering to red blood cells. The interaction between oxygen and iron in the hemoglobin. So now an example of ion-induced dipole force. Another one is ion dipole forces. Ion dipole force interactions are found in solutions of ions. When ionic compounds are dissolved in the polar molecules or polar solvents. So the strength of this force is what makes it possible for ionic substance to be dissolved in the polar solvents. Two types of ion dipole interaction there. Look at this. There are anions and the cations. Two types of ions are the cations and the anions. Anion, the interaction between anion and the polar molecule, the interaction between cation and the polar molecule. Examples for this is when sodium chloride dissolves in water by ion dipole interaction is taking place. The solubility of ions in the polar molecules, what we call ion dipole interaction. Look at this one. When sodium chloride is dissolved in water molecule. The positive ends of polar molecules are oriented towards the negatively charged ion. What's the negatively charged ion? Chloride. In this case, here we have sodium ion and the chloride ion. Chloride ion is anion, sodium ion is cation. You know that water is a polar molecule. Polar molecule. Water is a polar molecule. Water is a polar molecule. It has dipole moments. Partial negative, partial positive. Here are partial negative and partial positive. This is negative. Positive index of the polar molecule. What's the positive index of the polar molecule? Of the positive index of water? Hydrogen. Hydrogen index. Positive index of water molecule are oriented towards the negatively charged anion. There is attraction between the negatively charged anion and the positive index of the water molecule. There is an interaction between the hydrogen side to that of the chloride ion. And the negative index of polar molecules are oriented towards positively charged. Negatively charged index of polar molecule is this oxygen in water. So there is the attractive force between sodium ion and the oxygen side of the water molecule. This types of interaction is said to be ion dipole force. So in this case, there is interionic, and the attraction between molecules and the ions of this ionic compound or sodium chloride. So these types of forces, interaction force, makes this sodium chloride to be dissolved in water because there is interionic and intermolecular force, interionic force. So ion dipole force. So these types of ion dipole interaction makes some ionic compound to be dissolved in water. So some ionic compounds can be dissolved, just like sodium chloride and so can be dissolved in polar molecules because of interaction between ions and dipole forces, dipoles. What is the hydrogen bond? It's not a true bond, by the way. It requires hydrogen atom covalently bonded to strongly electronegative atoms. If hydrogen is bonded to strongly electronegative atoms, there will be a formation of hydrogen bond between the molecules. For example, fluorine, oxygen, and nitrogen are the most electronegative elements. Look at this. There is a hydrogen bond among the water molecules, between the water molecules, because there is interaction between the water molecules because of dipole force, another form of dipole force, hydrogen bonding. The interaction between the negative end of the water molecule to that of hydrogen side, because hydrogen attains partial positive, oxygen attains partial negative. The interaction between the two molecules is said to be hydrogen bond. Look at this. Electronegative atoms, nitrogen and oxygen. The interaction between ammonia and the water. The interaction between ammonia and the water is hydrogen bonding. Said to be hydrogen bond. Another examples. Covalent thermomolecular, hydrogen bond thermomolecular. The force between the intermolecular force between water molecules, hydrogen for ammonia molecules, water and ammonia molecules is some examples of hydrogen bonding. So finally, when this all kinds of interaction between the molecules, the solute and the solvent, solution can be formed. Unless otherwise, solution cannot be formed. That we call that like, dissolved like, and if there is force of interaction between the solute and the solvent, solution will form. Which of the following compound is likely to be more soluble in water? Compare this one. Compare the two molecules. Which of this molecule likely to be more soluble in water? What kind of intermolecular force between the water molecules and these molecules when these molecules are dissolved in water? The second question, what type of intermolecular force exists when the following pairs interact? The interaction between hydrogen bromide and hydrogen sulfide, chlorine molecule and carbon tetrabromide. Let's try to answer these two questions. You should have to compare the electronegativity of oxygen to that of sulfur. Which one has more electronegative value? Is it oxygen or sulfur? I think it is oxygen. So if it is oxygen, which of these compounds will likely to be dissolved more in water? The answer is this one, this molecule, because oxygen is more electronegative element than that of sulfur. There will be a strong hydrogen bonding between that alcohol and that substance to that of the water. So this is what type of intermolecular force exists when the following pairs interact together. The interaction between hydrogen bromide and hydrogen sulfide. What kinds of molecules are they? Are they polar, non-polar, dipole, dipole force? Because two molecules are polar. The force of interaction between two polar molecules is said to be dipole, dipole force. What about chlorine? Chlorine is non-polar. Carbon tetrabromide is also non-polar. You know how polarity is determined. So in the interaction between the two polar molecules is dipole force or London force. Iodine, ion. This is the interaction between an ion and a non-polar molecule. What kinds of force of interaction that can exist between the two? Ion induced dipole force. And this is ammonia and benzene. Benzene is non-polar. Ammonia molecule is polar. What kind of dipole induced dipole force will be? And so this is all about the way in which solutions come form. So the solution is formed when there is the similar intermolecular force between solvent and solid to that of solid and solid and solvent and solid. So it depends on the intermolecular force between solvent and solid. If the intermolecular force between the molecular force between the solid and solvent overcome the intermolecular force of solvent and solid, solution will be formed. This is how solution forms. Okay, the last and the fifth lesson in this part is seeing factors affecting solubility. Still you are on solubility. What factors affecting solubility? So there are conditions that affect solubilities. What are they? Let us see the factors. Factors that are affecting the dissolving process. The dissolving process. Some factors affect solubility. How much solute is dissolved. Some factors affecting the rates of solubility. How fast solute is dissolved in the solvent. And some factors affect the rate and both the rate and the solubility. Solubility. What is solubility? Solubility is the amount of solid that can be dissolved in the given solvent. In the given solvent. What about the rate? The rate at which solute is dissolved in the given solvent. How fast solute is dissolved in the solvent is what you call the rate. What factors determine this rate and the solubility of the solvent? Solubility of substance in a given solvent depends on this condition. What we see? Interparticle force, temperature, pressure, temperature and pressure for gases only. Solubility of a substance in a given solvent depends on interparticle forces, what we saw, what we have seen in the previous lesson. intermolecular interaction or interparticles interaction is one factor that determines the solids to be dissolved in the solvent, or determines the rate and the solubility, temperature and the pressure. These are the conditions. What is the effect of temperature on solubility of solids? Almost around 95% of solids, the solubility increases with temperature. In most cases, when solid is dissolved in liquid solvent, as temperature increases, solubility will also increase. So, for example, take ammonium nitrate in 100 milliliters of water. The solubility of ammonium nitrate in 100 milliliters of water is 118 grams at 0 degrees Celsius. And 811 grams will dissolve at 100 degrees Celsius. Look at the difference between. What will happen if temperature increases to the solubility of ammonium nitrates? The solubility of ammonium nitrates in 100 milliliters of water, this much amount of ammonium nitrate will completely dissolve it in 100 ml of water at 0 degrees Celsius. As temperature increases, the amount of ammonium nitrate increases. The solubility of ammonium nitrate increases. This is one examples of the effect of temperature on the solubility of most solids. So heat can be released or absorbed when ionic substances are dissolved in water. Not all. Almost 95% of solids, the rate of solubility and the solubility of substance solidity will increase as increasing temperature. You know that when the solution is formed, there is a change in the amount of it. That might be endothermic or exothermic. So many ionic solids dissolve by endothermic process. When many of the ionic compounds are dissolved, heat is absorbed from the surrounding. This process is said to be endothermic. Endothermic. Energy is absorbed. Their solubility in water usually increases as heat is added and the temperature increases. As temperature increases, the amount of solids that can be dissolved in a given solvent increases. Look at this one, this figure. This is the solubility. This is the temperature. Solubility versus temperature. Most of the substance increases, the solubility of substance increases as temperature increases. There are some substances, for example, take sodium sulfate to some amount until around 28 or 27 degrees Celsius, the solubility of sodium sulfate increases as temperature increases. But as temperature becomes higher and higher, the solubility will decrease. Why? As I have told you that most of the process is endothermic. Take another example here too. Sodium sulfates. As temperature increases, the solubility of this compound decreases. What happened? Let us see the case. For example, potassium chloride dissolves endothermically. The solubility of potassium chloride increases as temperature increases because more heat is available. Ammonium nitrate, so see, dissolved in water, the solution becomes very cold. The solution process is endothermic, this case too. So increasing with increasing temperature. A number of ionic compounds decrease in solubility with increasing temperature. Why? Because, for example, sodium sulfate, many liquids and the gas dissolve exothermically. In this process, instead of endothermic, the process is exothermic. Heat is released out to the surrounding. This is why the solubility of some compound decreases as temperature increases. The solubility usually decreases as temperature increases. The overall heat change or the energy change is exothermic. Energy is released for some compounds. For example, Solubility of sodium sulfate rises more than tenfold when temperature rises from 0 degrees Celsius to 32.4, where it reaches a maximum of 49.7 gram. The solubility of sodium sulfates is per 100 gram in water is decreasing because the process is exothermic. If the process is exothermic, solubility will decrease as temperature increases. This is the effect of temperature on the solubility. The effect of temperature on solubility of gases. What will happen if temperature increases to the solubility of gases? Let us see what will happen. Solubility of gases in solvent typically decreases with increasing temperature. Why? Why solubility decreases as increasing temperature for gaseous substance, gaseous solids? Why does solubility of gas in solution decreases? With increasing temperature. As temperature rises, the dissolved gas or air molecules begin to boil out. It escapes out from the system of the solution long before water itself boils. It boils out. As temperature increases, the concentration of gas dissolved in the solvent will decreases, and the gaseous molecules will escape or boils out. Heat is released when new attractive force between gas and solvent molecules form. So this is also exothermic. Look at these examples, this figure. Methane, oxygen, carbon dioxide, nitrogen, helium. The solubility of all gases or molecules decreases with increasing temperature. Increasing temperature. So gas in water, this is in water. If external heat is added to the system, it breaks the attractive force between the gas and the solvent. It decreases the attractive force between the gaseous molecules and the solvent molecule as temperature increases. So the interaction between the solvent molecule and the gaseous molecule will decrease as increasing temperature. This is why the solubility of gas decreases as increasing temperature. So decreases the solubility of the gas. This is so take for example the solubility of oxygen in water decreases by 34% from 0.041 gram per liter of water to 25 degrees to 0.027 gram per liter at 25 degrees. So rising temperature of rivers and the lakes, for example. Do you know what a thermal pollution is? When the temperature of water bodies rises, water bodies like rivers and the lakes, by dumping heated wastewater from industry, plants and nuclear power. This is called thermal pollution. The amount of oxygen dissolved in water will decrease as increasing the temperature of the water bodies. This is what we call thermal pollution that affects the aquatic life in water. What about the effect of pressure? Pressure has on the solubility of gas. Changing pressure has no appreciable effect on the solubility of solids and the liquids in liquids. But there's a concentration of, for example, the carbon dioxide in soda, it means Coca-Cola or Mirinda or Fanta or in other beverage. Does the concentration of carbon dioxide in soda increase or decrease when open the bottle? What will happen to the concentration of carbon dioxide when the bottle is opened? Do you see? When the bottle of Coca-Cola is opened, what will happen? When a can or a bottle of carbonated beverage is opened, the pressure on the surface of the beverage is reduced. Opening means reducing the pressure. As pressure reduced, the solubility of gas is also decreased. So on the surface of the beverage, reduced atmospheric pressure, much of the carbon dioxide bubbles out of the solution. So the concentration or the solubility of carbon dioxide decreases. look at this example. When the can or the Coca-Cola is open, you have seen form. Sudden release of pressure from a carbonated beverage. When this pressure is suddenly released, carbon dioxide is less soluble and excess bubbles from the solution is out. So the concentration of carbon dioxide in this carbonated beverage will decrease. That's decreasing the solubility. So increasing pressure increases the solubility of gases. Decreasing pressure, decreasing the solubility of gases. The concentration of gas will decrease. So look at this one, the difference between the two. Pressure 1, pressure 2. Pressure 1 is less than pressure 2. All gases become more soluble in liquid at a given temperature when the partial pressure of the gas over the solution is increased. There's the number of the molecule of gas above the solution, the number of molecules above the solution. The number of molecules above the solution is greater than the number of moles of above the solution on the second case. So as increasing pressure, more molecules will dissolve in the solvent as pressure is increased. So increasing pressure, increasing the solubility, increasing the concentration of gas molecules in the solution. So more gas particles will collide with the liquid surface and more gas will be dissolved. The same thing is true here. Gas above the liquid, dissolved gas, more and more gas particles enter the solution when the pressure is increasing from pressure 2 to pressure 1 to pressure 2. So this is dynamic law. Pressure increases, dynamic equilibrium will attain. Henry's law. What Henry's law says about the solubility of gases? What's the relationship between concentration and pressure? The quantitative relationship between pressure and the solubility of gas is described quantitatively by Henry's law. Henry's law, solubility of gas is directly proportional to the partial pressure above the solution. Partial pressure of gas above solution. If the partial pressure of gas above the solution increase, the solubility of gas will also increase. So it can be expressed symbolically by this formula. Concentration of gas is direct relationship to the pressure of gas above the solution, partial pressure. This is Henry's constant. So where gas is the concentration of dissolved gas at equilibrium, P gas is the partial pressure of the gas, in the case Henry's law constant. So the units of Henry's law constants are therefore molarity per times atmospheric pressure. If this partial pressure of gas changes, while the temperature remains constant, keeping the temperature remains constant, the new concentration of the gas within the liquid can be calculated by this formula. The relationship between concentration and the pressure, you can calculate the pressure and the amount of gas that can be dissolved in the given solvent at constant temperature. For example, what's the solubility of nitrogen gas at 25 degrees Celsius and 1000 is this? What is the concentration of nitrogen dissolved in water under atmospheric conditions? The partial pressure of nitrogen gas in the atmosphere is 0.78 atmosphere. Let us see the calculated amount of the dissolved amount of nitrogen gas. So in this case, therefore, if you use Henry's law, Henry's formula, the Henry's constant, calculate the Henry's constant is squared. Therefore, the solubility of nitrogen gas in water is at this pressure, at 0.78 atmosphere. What will happen if pressure is increased? And this, at 1 atmosphere, the solubility of gas, solubility is decreased or increased? Why? Solubility is decreased in this case. Solubility is decreased. The solubility of nitrogen gas is 6.8 times 10⁻⁴ mole per liter at 1 atmosphere. At 0.7 atmosphere, 5.3 times 10 raised to negative 4 molar. Which one is greater? Is it decreased or increased? Decreased. Why? Why it is decreased? Because pressure is decreased from 1 atmosphere to 0.8 atmosphere. So the decrease in solubility is the result of lowering the pressure from 1 atmosphere to 0.78 atmosphere. Do all gas obey Henry's law? According to Henry's law, increasing pressure, increasing solubility. Do all gas obey the Henry's law? Let us see. Gas that form strong intermolecular force, such as hydrogen bonding, react chemically with water. Hydrogen chloride, the hydrogen halides, hydrogen sulfide, ammonia do not obey Henry's law because there are hydrogen bonding in the molecules and intermolecular force between water and these polar molecules. They are polar molecules bonding or react chemically with water. So increasing or decreasing pressure may not affect the solubility. All these gases are much more soluble than predicted by Henry's law because there is a strong intermolecular force of attraction between the water solvent and this molecule. The gas with lowest value of Henry's law constants as highest concentration. So among nitrogen, oxygen, carbon dioxide is the lowest value of Henry's law constant. So let us see some questions. Which of the following factors has little effect on the solubility of liquids and solids? Pressure, temperature, intermolecular force, all. Which one has little effect? Solubility of liquids and solids. It is pressure. Pressure almost has no effect on the solubility of solids and liquids. The Henry's law constant, nitrogen, oxygen, carbon dioxide, and water are 1,600, 700, 800, 780, 29 atmosphere per molar, respectively. Which of these gases has the highest concentration in the sample of water at 25 degrees when the gas pressure over the water is 1 atmosphere? It is carbon dioxide. At a given temperature and pressure, nitrogen gas is more soluble in water than helium. Which one of them has a higher value of Henry's law constants? Nitrogen. The answer is nitrogen. At a given temperature and pressure, nitrogen gas is more soluble in water than helium. Which one of them has a higher value of K? Having a higher value of K means liter of water at 25 degrees dissolves this much amount of oxygen when the partial pressure of oxygen is 1 atmosphere. What is the solubility of oxygen from air in which the partial pressure of oxygen is 0.1 atmosphere? So you can compare the Henry's law relationship. When you're using Henry's law relationship, the amount of oxygen that can be dissolved is 8.484 times 10 raised to negative 6 grams in 1 liter. Thank you very much. That's all what you have for this part. See you next time. Goodbye.